All right, here we have quiz number 4, attempt number 1. We're looking at a 2.1 kilogram spaceship launched straight upwards from velocity of 0, or initial velocity of 0. We have a constant thrust of 38 newtons until it reaches a height of 21.2 meters, and then the thrust ends. We're ignoring air resistance, and then our objective is to determine the speed of the rocket when the thrust ends. So I did this actually in a few different ways. For momentum, we have the sum of forces with the integral of time. So basically you get the sum of forces times delta t, and that's with like an average as well, is equal to the change in momentum. So we have mv2 minus mv1, and we know that mv1 is equal to 0 because v1 is equal to 0. So we get the sum of the forces times delta t is equal to the mass times v2, and actually that is not right, but if you go down a bit, we do a free body diagram. We have our force of thrust, or thrust force going up, weight going down, and so we get T minus mg, because we don't have any air resistance, and T minus mg is equal to ma, and that allows us to find the acceleration while all those forces are at play, and our acceleration is equal to 8.285. And this is where you can kind of do a few different things. Using a few different kinematics, originally, you're supposed to use the energy and momentum methods, but from straight up kinematics, I went just with that equation, and I realized you could find the final velocity, which would be 18.74 meters per second. But then I just ended up using that as a benchmark, and so trying to use the momentum methods, we know our sum of forces, we don't know the final velocity, and we don't know the delta t yet. So using how far the rocket went, it plugged it into one of our kinematic equations, and x of 0 is equal to 0, v0, or initial velocity is equal to 0, so we get delta x is equal to 1/2 acceleration times time squared. And so t is equal to the square root of 2 times delta x over a, and we get t is equal to 2.26 seconds. Then if we go over here, sum of forces, T minus mg times delta t is equal to m v sub 2. And what you could also do here is if you divide by delta t on both sides, you would get acceleration average, which is right there. And here, again, we know it's constant. That's why we could use the kinematic equations. And we have everything except, well, now that we have the delta t from before, the only thing we don't have is the final velocity, or v2. And after plugging everything in, we get v2 is equal to 18.74 meters per second. Or we could do the final thing with energy, and we know at the beginning energy is equal to 0. We don't have any potential energy, we don't have any kinetic energy, but we do have work put into the system, that's U. And then by the end of this, we do have kinetic energy, and we have potential energy, because rocket starts here and it goes up for 21.2 meters. And so h is equal to 21.2. We have the force of thrust times the distance that it travels, because that is, again, 21.2 meters. Then we have the mass, gravity, distance traveled, so we can determine work. And yeah, it should look fairly similar to up here, actually. And we get our final velocity, again, equal to 18.74 meters per second. So with sig figs, we get 18.7 meters per second.